Suppose that x, which equals f of t, is given by this function 1/4 t squared minus t plus 2. And that denotes the position of a bus at some time t. Question, or part A, says find the velocity as a function of time and then plot its graph. So let's go ahead and find the velocity. And so the velocity is the change. Velocity is the change in position over the change in time. Okay. Now here for this particular problem, they're actually asking for, when they say velocity, they implied instantaneous velocity. So what we need is the limit as delta t goes to 0 of this guy, which we call lovingly dx dt, which is the same thing as f prime of t. Okay, so this is what we're looking for right here. So what we'll do is we'll differentiate this function. So f prime of t is equal to 2 times 1/4 times t minus 1 plus 0. So this is going to be 2 times 1/4 is 1/2. So 1/2 t minus 1. Now let's go ahead and plot that function. I'm going to go grab a straight edge. For this particular problem, we're probably not so concerned with t values over here that are negative. So if we let this be the t-axis, the time axis, and we let this be the position of the bus, okay, versus time, you know what, I'm going to extend this line down a little bit because we're going to get some negative values out here. Okay, we're probably not so concerned when time is negative. So let's look at this function. We know here's -1, here's 0, here's +1, +2, +3. Okay, now it doesn't really say what position, if it's in meters or whatnot, so let's just assume meters. Okay, who knows, maybe it's miles, I have no idea. Now this function right here is a y-intercept of -1, so I'm going to go ahead and plot that guy. It also has a slope of 1/2, so up 1 over 2. Okay, so let me start marking out. Here's 1, here's 2, here's 3, and so up 1 over 2 puts us right here. And so if we go ahead and we draw our graph in, this right here is our velocity as a function of time. So we'll probably write this velocity of the x variable as a function of time, just like that. Okay, so I should, when I said that this is the position, I said that wrong. This is, so let's make that correction. This is actually the velocity as a function of time. My mistake. Okay, now if we wanted to, we could also plot the position function. Okay, and what we're going to do in a minute is we're going to end up plotting the acceleration. Well, we're going to find the acceleration. I'll show you what the acceleration function looks like. So here's what I want you to notice. Velocity is changing over time. Velocity is not staying constant. It's like if you're in your vehicle, you're in your car, you know, and you're traveling, you're driving. If your velocity is constant, you're traveling at the same speed with the same direction. So think about it like if you're driving down, like, I don't know, Highway 59 towards downtown, okay, given no traffic. I don't know when you're going to find that, but so you're driving at a constant rate, right? And so if our car is driving, this is as good as the picture for the car gets, okay? So if our car is driving here at a constant velocity, we're not changing the speed. The speedometer is staying the same. Now, that's not the case for the bus here. The velocity is not the same, okay? It's changing over time. So the bus must be accelerating either in a positive or negative direction, okay? So this answers part A. Now let's go ahead and take a look at the question. I'm going to write it right over here. The question for part B. So B says find and plot the speed as a function of time. So we'll do that here in green. Well, the speed is just concerned with not necessarily direction, okay, just the overall amount of velocity. So speed, we'll define speed as the absolute value of the velocity function, okay? And so if we take the absolute value of this guy, anything that's positive stays where it is. So it'll look like, if I plot that, anything that's positive for velocity stays where it is. Anything that's negative reflects to become positive. So this guy comes up, this guy comes up, and so it looks something like this. It's just a reflection over this line. So now we've got our speed, which is the absolute value of the velocity function, just like that. And that's it. That's all you got to do. Now let's go ahead and look at the third question. Part C says find the acceleration. Okay. Now the acceleration is given by the derivative of the velocity. So acceleration, okay, which I'm gonna just denote. Let me see if they have anything in the book here for their acceleration function. No, they don't. They don't really have a good. Well, all they have, we can write it like this: acceleration is the derivative of velocity, the change in velocity with respect to time, which is f double prime of t. So basically we have to take the derivative. This means take the derivative of the velocity function, which is the derivative of the position. So it's the second derivative. So we need dv dt, or f double prime of t. So that's easy. We just differentiate this guy again. We differentiate this guy. We get positive 1/2. So our acceleration is constant, and we're consistently accelerating at 1/2. Okay, and again, we don't know what the units of measurement are. Okay, but we've got our acceleration.